Magnets are everywhere, inside your headphones, motors, computers, even electric cars. But have you ever wondered how they're made? And what makes neodymium magnets the most powerful in the world? Today, we're diving deep into the incredible science and industrial process behind how magnets are made. From raw elements to the strongest permanent magnets known to humanity. Before we dive into the fascinating world of magnets, take a moment to subscribe to our channel. We bring you deep behind-the-scenes looks at how the world's most amazing things are made. Every single week, hit that subscribe button and turn on the bell icon so you never miss an episode. Now, let's get started. Magnets are materials that produce a magnetic field, a force that can attract or repel certain metals like iron, nickel, and cobalt. There are several types of magnets: temporary, permanent, and electromagnets. But among permanent magnets, one type stands far above the rest in strength and performance: neodymium magnets. They're tiny but mighty, used in everything from wind turbines to hard drives and MRI machines. So what makes them so special? And how are they manufactured? Let's start at the source. Neodymium magnets are made from rare earth elements, mainly neodymium, Nd, iron, Fe, and boron, B. Despite the name, rare earths are fairly abundant in Earth's crust, but mining them is complicated and expensive. The raw neodymium is usually extracted from minerals like monazite and bastnasite, mostly found in China, Australia, and the United States. Once extracted, these elements are purified and transported to specialized magnet factories, where the real magic begins. At the factory, neodymium is combined with iron and boron to create an alloy called NdFeB, the base for high-performance magnets. The mixture is melted in vacuum induction furnaces at over 1,300 degrees Celsius, 2,372 degrees Fahrenheit. This molten metal is then rapidly cooled into thin ribbons through a process called strip casting. This step is critical. It locks the alloy into the right microstructure for high magnetic performance. Next, the brittle metal ribbons are crushed into powder. Ultrafine particles just a few microns wide. This powder is incredibly sensitive to air and moisture, so all handling is done in inert gas chambers to prevent oxidation. The powder is then transferred into a mold, where it's aligned using a strong magnetic field to orient the grains in the same direction. This step determines the direction of magnetism and is essential for maximizing strength. Once aligned, the powder is compressed under several tons of pressure into a solid but fragile compact called a green body. This compact is then heated in a sintering furnace at around 1,080 degrees Celsius, 176 degrees Fahrenheit, causing the particles to fuse into a dense, hard magnet. After sintering, the magnets are cooled and undergo precision grinding to reach their final shape, usually discs, blocks, or rings. But we're not done yet. Neodymium magnets are prone to corrosion, so they're coated with nickel, epoxy, or zinc for protection. The final and most crucial step is magnetization. The magnet is placed inside a pulse magnetizer, a machine that generates a massive electromagnetic field. In an instant, the material becomes a powerful magnet, capable of lifting weights hundreds of times its own. Neodymium magnets are already impressive, but researchers have taken it even further. At the National High Magnetic Field Laboratory in the US, scientists created a hybrid magnet that reached an incredible 45 Teslas of magnetic field strength, making it the most powerful magnet in the world. This hybrid uses both superconducting magnets and resistive magnets in tandem. It's used for cutting-edge research in physics, chemistry, and materials science. In industry, neodymium magnets are essential for high-performance motors, medical equipment, and even space tech. Despite their size, neodymium magnets are not toys. They can snap together with such force that they can break bones or shatter on impact. They're also a serious risk if swallowed, especially for children. In manufacturing, strict safety measures are followed, including magnetic shielding, robotic handling, and controlled storage. As demand for electric vehicles, wind turbines, and high-tech electronics grows, so does the demand for powerful, efficient magnets. But the reliance on rare earth elements raises environmental and geopolitical concerns. That's why researchers are exploring recycling old magnets, developing alternatives, and improving the sustainability of magnet production. The goal: to build a cleaner, greener future, powered by the invisible force of magnetism. These small but mighty components power our modern world, and their story is still being written. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe for more behind-the-scenes looks at how our world is made. Every second, somewhere in the world, a light turns on, a signal is sent, a machine begins to hum, and behind it all is one unassuming component: the cable. From towering skyscrapers to underground data vaults, from electric vehicles to the smartphone in your hand, cables are the silent veins of modern civilization. But have you ever stopped to wonder, how do we make the things that make everything else work? How does raw metal become a lifeline of power and communication? In this documentary, we'll take you deep inside one of the most advanced cable manufacturing plants on Earth. A place where molten copper becomes signal, where plastic polymers wrap precision, and where every strand is tested, measured, and trusted. It's a world of heat, pressure, and accuracy, where a fraction of a millimeter can mean success or failure. If you're fascinated by the industrial backbone of modern life, don't forget to subscribe to Top Discovery 4K. We dive into the science, scale, and secrets behind the objects you use every day without even knowing it. Now, let's follow the journey of the cable, from copper to connectivity. Before a cable transmits power or data, before it's wrapped in layers of armor or plastic, it begins life as something raw, heavy, and silent: metal. At the heart of almost every modern cable lies one of two core elements: copper, the gold standard of conductivity; aluminum, lightweight, economical, and strong. Both metals are delivered to the factory in massive coils or rods, thick as a thumb and heavy as memory. These coils can weigh up to 5,000 kilograms each, and are often delivered straight from foundries or recycled from scrap processing plants. But this isn't just about melting and molding. Making a cable starts with purity. Even a trace of oxygen or iron in the copper can reduce its performance dramatically, resulting in heat loss, weak signals, or worse, electrical failure. That's why premium cable manufacturers start with oxygen-free copper or electrolytic tough pitch copper, refined to over 99.99% purity. The goal: maximum conductivity, minimum resistance. And if aluminum is chosen, it's not the foil in your kitchen. This is industrial-grade aluminum, often alloyed with small amounts of magnesium or silicon for strength, then treated to resist oxidation. But conductors are only half the story. Wrapped around them will be layers of insulation, shielding, and jacketing, each made from custom polymers: PVC, polyvinyl chloride, flexible, fire-resistant, and inexpensive; XLPE, cross-linked polyethylene, tougher, more heat-resistant; TPE, nylon polyurethane, used in specialty or extreme environment cables. These plastics arrive in the form of pellets, small as lentils, stored in silos and fed into the process by vacuum systems and gravity hoppers. Colorants are added too, often vivid reds, blues, and yellows, to help identify individual wires inside a multi-core cable. Even color has a code here. Even color has a job. And finally, for heavy-duty cables, there's steel, either galvanized or stainless, used for armoring. Because in some places, a cable has to fight off water, pressure, fire, rodents, even time. All these materials, metal, plastic, steel, will soon come together to form something far greater than the sum of its parts. But first, the copper must be transformed. Coming up next, how a thick, stubborn rod of copper becomes a hair-thin wire that can carry electricity across continents. The copper arrives thick, solid, and unforgiving, coiled like a metal python, waiting to be tamed. But no cable can use copper in this raw state. It's too thick to bend, too coarse to carry precise signals. To become useful, it must first become thin, very thin. This is where the magic of wire drawing begins. The process looks deceptively simple. A copper rod is pulled through a series of holes, each one smaller than the last. But these aren't ordinary holes. They're precision-engineered tungsten carbide dies, hardened, polished, and set in perfect alignment. Each pass through a die stretches the copper, reducing its diameter and extending its length. From 8 millimeters to 4, then 2, then 0.5. Eventually, the copper is drawn down to just a fraction of a millimeter thick. Thinner than a sewing needle, yet perfectly uniform. But copper is stubborn. As it's drawn, it hardens. Too much tension and the wire snaps. Too much heat, and it warps. So factories use emulsified lubricants, a milky solution that cools the wire and protects the dies. Without this, the dies would wear out in hours instead of weeks. And still, the process isn't done. Once the copper has been drawn to its final diameter, it passes through a continuous annealing furnace, a glowing tunnel of controlled heat. At around 400 to 500 degrees Celsius, the copper is softened at the atomic level. Its internal grain structure relaxes. The wire becomes more ductile, easier to bend, twist, and coil without breaking. This transformation, from stiff rod to soft, flexible wire, happens at speeds of up to 40 meters per second. Out the other end, the wire is cooled, dried, and wound onto take-up spools. Neat, gleaming coils that look almost like polished hair. Each spool is tagged, logged, and ready. What was once a chunk of metal is now a high-performance conductor, ready to carry power, data, or both. But most cables don't use just one strand. They use many. A single wire is useful, but in the world of electricity and communication, strength comes in numbers. That's why most cables don't use just one strand. They use several, twisted together in precise geometries that balance strength, flexibility, and signal integrity. This is where the process known as stranding begins. Inside a massive, rotating machine, resembling a mechanical spider, the individual wires from the previous step are drawn into formation. One by one, they're spun together, spiraling into a conductor bundle. But this isn't random twisting. The number of strands, the pitch of the spiral, and even the direction of rotation are carefully calculated, down to the millimeter. Why? Because how wires are twisted determines how electricity moves. It affects everything from electromagnetic resistance to heat dissipation. In power cables, stranding adds flexibility and ensures the cable doesn't break when bent or coiled. In communication cables, such as Ethernet or telephone lines, pairs of wires are twisted in exact ratios to reduce crosstalk, that annoying interference that garbles sound or data. Some cables use just 7 strands. Others, like high-capacity power lines, may use 37, 61, or more, layered concentrically for maximum flow. And then there's pairing. For multi-core cables, each twisted pair is given a unique color combination: red and black, green and yellow, blue and white. These colors follow strict international codes, allowing electricians and technicians to identify, repair, or install without guesswork. Once twisted, the strands pass through binders, thin tapes of polyester or nylon that hold the bundle tightly together. From this point forward, the conductor acts as one unit. Bending it no longer stresses a single strand. Twisting it no longer weakens the core. It becomes a unified body, the beating heart of the cable. But this heart is still vulnerable. Bare copper cannot survive the real world. It needs skin. It needs armor. Electricity is powerful, but without control, it's also dangerous. That's why every conductor, no matter how small, needs insulation. This isn't just wrapping wire in plastic. It's engineering a barrier between raw energy and everything else around it. Moisture, metal, people, the air itself. At this stage, the freshly stranded conductor enters one of the most sophisticated machines in the entire factory, the extrusion line. Here's how it works. First, plastic pellets, stored in tall silos, are vacuum-fed into a hopper. These tiny beads, made of PVC, XLP, or Teflon, are then melted at over 200 degrees Celsius, forming a thick, molten polymer soup. The molten plastic is pushed through an extrusion die, a tool shaped exactly like the cross-section of the final cable. The die surrounds the conductor with a perfectly centered layer of insulation, applied in a single, continuous flow. There's no stitching, no glue, just heat, pressure, and absolute precision. But the moment the plastic hits air, it starts to cool. To To prevent cracking, bubbles, or uneven shrinkage, the insulated wire is immediately submerged into a water trough, chilled and calibrated to control the cooling curve. What emerges is more than just wire with a coat. It's a functionally advanced material, tailored to resist heat, water, voltage surges, UV radiation, chemicals, and oils. Different applications demand different insulations. In homes, flexible PVC, safe and affordable. In high-voltage lines, cross-linked polyethylene, XLPE, heat-tolerant and tough. In hospitals or aircraft, low-smoke, halogen-free compounds to protect lives in case of fire. To the naked eye, it might just look like plastic, but under a microscope, it's a shield, a seal, a silent protector of energy in motion. And every detail matters. Laser gauges along the line measure the insulation thickness 1,000 times per second. If it's even a hair too thin, the cable is stopped, flagged, and reprocessed. Because when you're carrying thousands of volts through a concrete wall or data through a server farm, there's no room for error. Armoring turns a cable into a mechanical survivor, capable of withstanding crushing force, chemical exposure, and even gnawing rodents. To do this, the cable passes through another machine that wraps it in layers of galvanized steel wires, corrugated metal tape, or even stainless steel strips. These metal jackets are applied helically or longitudinally, depending on whether flexibility or maximum protection is required. For marine applications, the cable may also be layered with bitumen, jute, or waterproof polymers, designed to survive decades under the seabed, wrapped in mud, salt, and silence. In some cases, armored cables are also fire-rated, built to withstand 950 degrees Celsius for 2 hours without losing power transmission. These are the kinds of cables you see in nuclear plants, subway tunnels, and military command centers. By now, the cable is internally complete. It has a core conductor, insulation, shielding, and armor, but it still needs one last thing: a skin, something to hold everything together, something the world will actually see. The outermost layer of a cable is more than just a wrapper. It's the first line of defense against weather, wear, chemicals, and time. This layer is known as the jacket, and it's applied through the same high-speed technology that once insulated the core: extrusion. Pellets of PVC, PO, polyurethane, or low-smoke zero-halogen compounds are fed into a hopper, melted, and forced through a die. But this time, the die is wider, designed to slide the molten polymer over the entire structure of the cable, like a glove. As it coats the cable, the polymer fuses tightly, locking all the inner layers into one solid, sealed unit. The newly jacketed cable then passes through a cooling trough, where precise water jets harden the jacket without warping it. Sensors track every detail: diameter, centering, thickness, even surface texture. Depending on the application, the jacket may be glossy for low-friction installations, textured for grip and abrasion resistance, color-coded for voltage, function, or brand. In many cases, an inkjet printer adds vital markings along the length: voltage rating, conductor size, flame class, standards met, production date, and meter markings, critical for installers in the field. At this point, the cable is sealed, protected, and ready to face the world. But it's not quite finished yet. As the cable exits the jacket extrusion line, it moves at speeds up to 80 meters per minute, a blur of engineered material. But precision doesn't stop just because production is almost over. The cable now enters a final cooling stage, using calibrated water baths and forced air dryers to stabilize shape and material hardness. This ensures it won't deform during spooling, shipping, or installation. Then comes the printing station, where non-contact inkjet systems mark every meter with real-time data. Production lot, plant location, quality inspector ID, compliance logos, UL, CE, ISO. These markings turn each meter of cable into a traceable component, auditable down to the minute it was made. Next, the cable is cut, either into standardized industrial lengths, like 100 meters or 305 meters, or wound onto massive steel or wooden reels for long-haul applications. Each reel can weigh up to 5 tons, especially for medium voltage or armored cables. Finally, every reel is wrapped, strapped, and tagged, ready for its most important test of all. Before a single cable leaves the facility, it must prove itself. Every batch goes through rigorous testing in specialized labs, each test designed to simulate a worst-case scenario. High-voltage dielectric test, subjecting cables to 1,000 plus volts to verify insulation integrity. Conductor resistance test, ensuring the wire carries current within strict ohmic limits. Flame retardancy test, burning sections of cable in vertical chambers to ensure self-extinguishing properties.